Let's dive right into this explainer, shall we? Today, we are unpacking the absolute gold standard for line pipe integrity, API Specification 5L. If you've ever looked at miles of steel piping and wondered, how on earth does the energy industry guarantee that this stuff won't just burst under immense pressure or extreme environments? Well, the answer is right here. It all boils down to this incredibly rigorous QA and QC blueprint we're looking at today. Let's get into it.
So here is our roadmap for making sense of this massive standard. We're going to start big with decoding inspection frequencies, then move into locating your test samples, preparing the actual test pieces, and finally executing the mechanical tests themselves.
But real quick, before we break all that down, I want you to keep one thing in mind. This spec, it's basically a high-stakes recipe for preventing pipeline disasters. We aren't just talking about arbitrary numbers or polite suggestions on a page. No way. Every single pull, every bend, every microscopic inspection, it's literally the wall standing between safe energy transport and a catastrophic failure out in the field. High stakes, right? All right, Section 1. Decoding inspection frequencies. Or basically just knowing when to test. We have to figure out exactly how often you need to pull from your batches of steel pipe to maintain absolute confidence in their integrity.
Now, it's actually fascinating how this works. You've got universal tests, right? Take hydrostatic pressure testing. Whether you are dealing with the baseline product specification level 1 or the much stricter level 2, every single pipe gets pumped full of water and pressurized to absolutely prove it won't leak. But then contrast that with tensile testing, which measures the steel's strength. You obviously can't pull every single pipe apart. You'd literally have no pipe left to sell. So instead, the testing frequency changes dynamically. It scales up or down based on the pipe's specific dimensions, how it was manufactured, and that PSL tier.
The rules here brilliantly adapt to risk and scale. If you're an inspector looking at PSL2 tensile testing for the pipe body, you'll see that as your pipe diameter increases, your test units actually shrink. That means way more frequent sampling. For example, for a smaller pipe, say under 141.3 millimeters, you can group up to 400 pipes together and just test one sample. But the moment that diameter grows past 323.9 millimeters, well, the stakes are higher, the volume of steel is way larger, and your test unit drops to a maximum of just 100 pipes. Basically, bigger pipe means a much tighter testing net.
Okay, moving right along to Section 2, locating your test samples. Once your frequencies are set, you have to go harvest your ingredients, finding the exact right cut. And extracting these samples isn't just a free-for-all. You have to perfectly distinguish between longitudinal and transverse cuts based on the seam type. So L is for your longitudinal samples, cut parallel to the pipe's length, and T is for transverse, cut straight across it. The orientation of the metal grain plus the specific stresses that pipe is going to face absolutely dictate how you need to orient this cut.
So, the really crucial takeaway here is that your extraction coordinates are strictly dictated by how the pipe was manufactured. Take a seamless, non-cold expanded pipe, for instance. That takes tensile samples longitudinally. But actually, scratch that. If that exact same seamless pipe is cold expanded, the whole standard shifts and you have to take transverse samples instead. Or if you're looking at high-frequency welded pipes, you need 3 transverse samples taken at 90 degrees to the longitudinal weld for your impact tests. The point is, you can't just hack a random piece off the end. You have to surgically extract pieces that reflect the true structural DNA of that specific pipe.
And this methodology gets even more microscopic when we talk about Sharpie impact testing, which measures exactly how much energy the steel can absorb before it just completely fractures. Here, location is everything. Depending on the spec, you have to precision target either the heat-affected zone, that highly stressed area right next to the fusion line, or the direct center line of the weld bead itself. Millimeters literally matter here. If your notch is even slightly off-center, your test results are pretty much completely meaningless.
Which brings us to Section 3, preparing the test pieces. Now that we have our rough samples carefully mapped out and extracted, we need to set up for success before any mechanical stress is actually applied.
You absolutely have to follow this exact step-by-step procedure for Sharpie V-notch prep, especially the etching part before notching. It ensures you are actually testing the absolute weakest microscopic point of the metal. First, you pull the specimen from as close to the outside diameter as practical. Then you etch the steel. This is a chemical process that visually reveals the exact structure of the weld and that heat-affected zone we just talked about. And only after etching can you precisely locate the notch axis. You are quite literally making the invisible visible just to make sure the physical test breaks the metal exactly where it's most vulnerable.
Now, if you are conducting flattening tests, your sample prep kinda branches out.
It depends on whether you are dealing with multiple lengths of pipe from a continuous coil, single lengths, or specific grades. Like if you're pulling from a continuous coil, you're grabbing pieces from the coil ends and the weld stops. But if it's single, non-expanded lengths, you grab pieces from each pipe end. It's smart because the standard perfectly adapts the preparation to the actual reality of the manufacturing line.
Check this out for guided bend test pieces on submerged arc welded and combination welded pipe. The spec is incredibly strict here. The weld reinforcement must be completely removed from both faces before the test even begins. The long edges have to be machined or oxygen cut so they are perfectly smooth. Why? Because you really don't want the bulky geometry of a bulging weld bead throwing off a test that's designed to measure the underlying ductility of the joint. That surface has got to be totally flush.
All right, finally, Section 4, Executing the Mechanical Tests. This is the climax of the whole quality control journey, the actual cooking instructions, where we put the steel to the ultimate test and push it to failure.
Now, what's really fascinating to me about this part is that API Spec 5L doesn't try to reinvent the wheel with its own testing physics. Instead, it rigidly points you straight towards specific ISO and ASTM standards to carry out the physical drops, pulls, and crushes. Tensile testing? Go look at ISO 68921 or ASTM A370. Charpy Impact? ASTM A370 or ISO 148-1. API gives you the ultra-strict framework for when and where to test, but it relies entirely on these globally harmonized engineering standards to dictate exactly how the machines operate. It's a massive collaborative effort.
And that strict framework applies directly to the guided bend test. Here, you use a highly specialized plunger-type jig to apply uniform, perfectly calculated stress. You aren't just bending the steel randomly. The mandrel radius and the die radius are meticulously calculated using a very specific strain formula based on the pipe's diameter and wall thickness. Everything is locked down and controlled, which means the test is perfectly repeatable, whether that pipe is sitting in a lab in Texas, Tokyo, or anywhere else in the world.
The actual execution of that bend, it is absolutely unyielding. It's critical that one test piece is bent with the root of the weld facing directly against the mandrel, and a second piece is tested face down. Both pieces get forced into this brutal, severe 180-degree U-shape. Doing it this way ensures that both the top and the bottom structures of that weld joint can survive extreme deformation without cracking wide open.
Okay, I want you to lock an incredibly important number into your head, especially if you're ever inspecting cold-formed welded pipe. Ready? 50 millimeters. It is a critical threshold.
So, why does that 50 millimeter mark matter so much? Well, if you visually detect a hard spot on a cold-formed welded pipe and it exceeds 50 millimeters in any direction, you are immediately required to deploy portable hardness testing equipment to verify what's going on in that zone. Hard spots can be brittle, and in this industry, brittle means it can fracture under pressure. The standard does not let you just eyeball a giant anomaly and wave it through. That 50 millimeter mark is exactly where a visual inspection rigidly escalates into hard mechanical verification.
And for our final quality check, specifically for submerged arc welded and combination welded pipes, macrographic testing steps in. You use this to verify that the internal and external welds are perfectly, flawlessly aligned. You are essentially taking a cross-sectional snapshot of the pipe wall. If the inside weld bead doesn't perfectly fuse and align with the outside weld bead, the integrity of the whole pipe is compromised. This macrographic test is your visual proof that the chemistry and the geometry of the weld are perfectly sound all the way through the steel. So, what does this all mean? Ultimately, it asks the big question. Is your pipeline's integrity left to chance, or is it proven by the book? Following every single frequency, every careful cut, and every brutal bend in API 5L is literally the only way to answer that with absolute certainty. This standard doesn't just assume quality, it proves it. Mathematically, mechanically, test by test. I really hope this explainer has given you a newfound appreciation for the meticulous science keeping our energy infrastructures safe. Thanks so much for learning with me today.